The way we can do this is by moving all of our control electronics to a separate chip, and then we can sort of sandwich these chips together in a flip chip architecture. This gives us a lot of control over the qubits without too much crosstalk overhead. Okay, so what does this all give us? So natively, this chip realizes a Bose-Hubbard Hamiltonian. So there's an on-site energy. This on-site energy is tunable. So using flux, we can individually tune this for every qubit. There's an anharmonicity because these are qubits, not linear resonators, and the anharmonicity plays the role of a Hubbard U. And then lastly, there's nearest neighbor coupling. This is transverse coupling, so it looks like kind of a hopping term for type writing Hamiltonian. Now, in our chip, we work in a limit where the Hubbard U is substantially larger than the nearest neighbor hopping term. And what this means is we can sort of project out double line excitations in the system and work in a hardcore limit. Okay, so essentially we can replace the bosonic operators just with Pauling matrices. Now, to make this state preparation technique possible, I want to add one more ingredient to this Hamiltonian, which is a drive. So we connect all of our qubits to a common drive. We drive the qubits very close to the resonant frequency. This populates excitation throughout the lattice. And one thing to point out is we can control the intensity of the drive through this parameter omega. It couples a little bit differently to every qubit, but we see that as a benefit. Helps us generate more entanglement. And then we can also detune that drive from a resonance with the qubits. I'm going to call this parameter delta, and this is going to be very important on this experiment. Okay, so let's look at the actual protocol. What does the sequence do? So we're going to start by separating all the qubits in energy and preparing a vacuum state, and then we're going to bring the qubits all together in resonance with each other and turn on this drive. After some time t, there'll be excitations in the lattice, there'll be some entanglement, and we're going to separate the qubits again. That effectively turns off the interactions, and then we can measure the qubits. Our measurements natively are at the z basis, so the population measurements, but we can also apply tomography pulses beforehand to extract other Pauling matrices. Now, this whole procedure happens relatively fast. We can do thousands of experiments in 1 second, and this allows us to do full-state tomography of relatively large subsystems. So in this experiment, we're going to be doing subsystem full-state tomography up to size 6 qubits. To make this a little bit more concrete, here's a plot of population, average population across the whole lattice throughout or versus evolution time. And so you can see that very quickly we start generating excitations. The harder we drive, the faster we generate excitations. But very quickly, when this tuning parameter is 0, so the drive is resonant with the qubits, very quickly we get 8 excitations. There's 16 qubits in the lattice, so that means we have one average half filling the lattice, so you can think of this like an infinite temperature state. Okay, so let's look at what this does. This is the spectrum of our whole Hamiltonian. There's about 60,000 states in here, and I've broken them out in terms of the particle number on the x-axis. So you can see that there's the highest density of states at about 0 energy and half filling, sort of in the center of the spectrum. So when we do this experimental protocol, at the end of this evolution time, we populate some swath of the spectrum. If the detuning of the drive is 0, the swath is centered around 0 energy. But we don't populate a definite state. We actually kind of populate every state. It's a non-determinate state, both in terms of energy and particle number. So it's a huge superposition state. Okay. But what we can do now is leverage this detuning of the drive. And when we do so, we'll populate slightly different states. So we can move the swath of the spectrum that we're populating up or down. And this allows us to sort of control are we looking at the center of the spectrum or the band edges. Okay, what are we going to do with this state preparation technique? Let's start looking at how entropy works. So in this experiment, we want to consider entropy between some subsystem of the lattice and its complement in the larger array. Of course, there can be entanglement between the system and the environment, but it turns out to be relatively negligible for this experiment. And that's just because we're working fast compared to the coherence times. We need to quantify the entanglement. To do so, we're going to use an entropic measure. Here we choose the second Renyi entropy, but that's not particularly important for the conclusions. And what we want to do is consider how this scales with different subsystems. So we can characterize a given subsystem by its volume, which here is just the number of qubits in it, and its area, which here is just the number of nearest neighbor bonds between the subsystem and its complement. And what we want to do is measure how the entanglement scales. Maybe it scales like a volume law, maybe it scales like an area law. And what we're going to do is use, like I said before, full state tomography of subsystems. We choose many subsystems, reconstruct the density matrices for all of them, and then we can extract entropy scale. Okay, now here's the data. So what you can see here is that the entropy of the subsystems grows as a function of system volume. And when we prepare states at 0 to tuning, we can see that there's a very rapid and almost linear growth of entanglement. And as we add some tuning of the drive, so we're populating closer to the band edges, then we see a more sublinear scaling, slower scaling of entropy. Now, this aligns pretty well with what we expect. So when we populate the center of the spectrum, we expect to excite sort of infinite temperature state, so volume law entanglement state. So we should see sort of the small volume limit of the famous P curve. But something different is happening when we populate states closer to the edge of the band. So let's investigate that a little bit more. So to do that, let's sort of linearize the problem. So let's assume that the overall entropy is just a linear combination of the subsystem's area and volume. And now if we can extract these parameters by linear fitting, we can learn something about the system. So here's the result of that linear fit. We can see that there's a relatively large volume contribution across the whole spectrum. And then when we go close to the center of the spectrum, the area contribution drops out. And this is the main result of our paper. So if we take the ratio of these two parameters, or fit extractions, we can really clearly see that there's a volume law state for states in the center of the band, and then states closer to the edge of the band have something closer to an area law like state. Okay, so with that, I'd like to conclude. So there's two things about this experiment that really excite me. One is the state preparation technique. So traditionally, state preparation techniques really struggle to generate states with really high amounts of entanglement. Typically, deterministic state preparation techniques are really best for states kind of near band edges. Now, we sacrificed determinism in our state preparation, but we got back that we could excite really all states in the entire spectrum. And then using this, we were able to show that the post-upward spectrum has this kind of crossover from a volume law entanglement to an area length entanglement spectrum behavior. So if you're interested, please check out our paper. It's an archive, and I skipped a lot. There's a lot more into it. Yeah. In the last minute of the talk, I want to just talk briefly about kind of extensions, where we can go from here. So in this experiment, we've really only leveraged a small fraction of the power of superconducting processors. And the reason is we have independent XYZ control all the time over all qubits. So what can we do with this? Let me just motivate two possibilities. So the first is quantum punches. So imagine we do the same experiment, except we start with half the lattice off. So we populate a huge entangled state in half the lattice. We bring the other half of the lattice back into resonance. And now we're able to watch, in the time domain, entanglement propagate into this formerly unoccupied part of the lattice. The second thing is we can add disorders. So we do the exact same experiment, but manually change the energy of every site. And now we can look at how disorder slows down the generation of entanglement and see whether we still can get volume law entanglement out of this. Okay, so with that, I'd like to conclude. Thank you for your attention, and thank you to my incredible group.
Thank you. I'm just curious to know, you have a lot of entanglement, but you don't really know where it is, right? Is it useful? Like what? I don't understand exactly how is that entanglement going to be useful. Could you give me some insight about that?
Yeah, maybe can I ask, when you say useful, in what context do you mean that? Do you mean like technical?
Well, why are you generating it? Like I don't understand like the long-term goal of why do you want that entanglement?
Yeah, that's fair. Well, I mean, I view this study more as a scientific endeavor than a technological endeavor. There's been a fundamental question for a long time in the field. I mean, frankly, the larger question is quantum mechanics commensurate with thermodynamics? Can we get eigenstate generalization? Now, this is a small system, and it's something that we can and did simulate on a classical computer. It takes about an hour to run one simulation on a desktop. But if we scale this up to larger system size, this will become an intractable problem. And I think learning about how entanglement scales in that context can give us useful information about ETH.
Great, yeah, I'm also interested in that question. I was just curious if there was some other secret. This would be great because it would give us this power. But I'm totally behind the science part. Thank you.
Hello, it's a very good talk, and I have a question about state tomography. So, you use the state tomography to calculate the entropy, but how to distinguish whether the entropy is from entanglement or just from the noise? I mean, the mixed noise.
Yeah, that's a great question. So that's a good point. So, for example, if our interaction time was a lot slower, and the time of this experiment was comparable to the coherence time, then the entanglement we measured would really just be mixed, with the environment. But we're working on a limit where the coherence time is about 10 times longer than the experimental duration, and so we think most of the entanglement really is between a system, a subsystem, and the complement within the array. And to quantify this a little bit better, we actually did kind of make some estimated upper bounds for how much of this entanglement is the so-called classical entanglement with the environment, and it turns out to be relatively small. Yeah.
Thank you.
We have a question here. Hi, great talk. So you see this gradual kind of movement between area law scale and entanglement and volume law entanglement. And why do you think you're not seeing a more clear phase transition? Is it because of the system size? Is it a fundamental property of the Hamiltonian? Something like that.
That's a great question. So first of all, the states we're preparing are not deterministic. So if I go back to that's perfect. Yeah, I'll go back to this slide. So the states we're generating, rather than looking at one eigenstate at a time, we're looking at a superposition of whole swap, and that swap has some bandwidth. The bandwidth is set by the amplitude of the drive, and so for that reason, we're sort of smearing out the physics a little bit. Okay, so that's maybe can be seen as a drawback of the experiment. But the other thing I'd ask is if we really would expect a phase transition in entanglement scaling, just given this particular Hamiltonian. I actually don't know the answer to that. It's a good question. Unfortunately, this is a finite size system, so it will never be a true phase transition. But I don't know in larger systems in the thermodynamic limit if there's a transition of that.
Hi, thank you for the wonderful talk. Just basic question, in this kind of setup, what kind of a type of cross-current strength can you achieve with a reasonable entanglement with this many atoms?
Yeah, sorry, what strength do you say?
Like coupling strength.
Coupling strength, okay. Just in terms of our native Hamiltonian? Yeah, great question. Yeah, so in this case, to put this in real units, the nearest neighbor coupling strength is 6 megahertz, and the next nearest neighbor coupling is typically around a few hundred kilohertz. And so that's the time of thermalization in the system.
So how small can you make U? So you can look at some like bosonic dynamics. So you could do analog, right? So you can get all kinds maybe.
That's a great question. So in principle, we can make it 0 because we fabricate linear resonators. That was done a long time before we had access first to transform qubits. The problem is there's a little bit we sacrifice when making linear resonators. So we would sacrifice in general flux tunability. We'd also sacrifice the ability to do digital gates, which would inhibit our ability to do tomography. But in principle, there are ways to kind of get middle grounds or even tunability between the qubit and a linear resonator. A few years like that.
In different transmons, you can lower it and raise it separately individually.
In principle, yeah.
Okay. Good, so if there's no other questions, then let's thank Ilan again for a nice talk.